Hello, a good day to you. If you're there, it's because you are curious, you want to know a bit more about quantum computing, and that is the idea of this video. This video is a translation of a talk that I did in Spanish, a pod science talk to try to present this new technology to people that is not familiarized with the area. So right now, what you are listening to is the translation of this talk to English, okay? First, the talk is going to be divided in two parts. A first part is really the presentation part. We're going to talk about quantum computing, what are their main characteristics that make it special, and why we need it, from where it comes this idea. And we're going to have a last part that is to show you what are the real life applications of this technology. In the middle, and it's going to be a bit short, and that's why I decided to call it interlude, we are going to talk a bit about the limitations, the current limitations of the technology. We are not going to spend so much time into that part by two reasons. The first reason is because I want this talk to finish in a positive tone, but by the other side is because I think that that topic deserves a whole different and only pod science talk about that or a more serious talk even. So that's why I prefer just to mention it briefly for you to have the idea about that. So, okay, very quickly about me. My name is Carolina Perdomo. I am 30 years old. I am from Venezuela. I did my, well, obviously I am from Venezuela. I think for my accent, you can recognize it. I did my PhD in the Universidade Federal do ABC in Brazil. And I worked in theoretical particle physics. And I did my master in the Université Paris in France, where I did experimental particle physics. Most of all, no? Currently, I am still in France and I am doing an internship in data science. More important than that, I am a woman. I am super curious about new technologies, especially right now quantum computing and in what has been these last 5 years. And that's why this summer I decided to participate in a summer program that is called the Womanium by that is a foundation in the USA that is precisely to try to give these tools to people for them to know more about quantum computing, to know how to communicate about that, and to know how to use it. So inside the Womanium, one of the things that I am trying to do also is precisely try to bring this technology to new people, and that's why I decided to organize this talk. In particular, I am doing this also in Spanish with little girls in a project that is called Quantum Chamitas. You can check more about that in my personal blog or in the YouTube channel. But in any case, it's for you to have idea an idea from what this come from and who am I that is the person that is talking. Okay, so well, without taking too much time, let's start. I want to start with a little curiosity. We are in the era of information. Everything, you can have it super fast. For example, if you take like a little golf ball, you can uh, put that in Google and suddenly you're going to have a bunch of results where you can know how many holes, dimples these little balls has depending on the country, okay? But sometimes we think that everything actually is that fast and totally is not like that. So for example, and I let you with this curious question, like how long do you think it takes to study the aerodynamic of a golf ball? Like how much do you think it takes to do a simulation of the airflow in the golf ball, for example? Well, I will let you the reference so you can go and read it, but that actually takes a bit of time, no? When we talk about 96 hours, we are talking about 4 days. For this experiment, they use a technique that is called like the grid mesh based method to study this problem, and they study in two particular limits of their airflow around the ball. But the interesting part about that is that one of the things that I notice is that when you do like the integration of the airflow into into the machine that is doing the simulation of that, it takes a lot of time actually, very very lot of time, and that is precisely something that I want to bring you into your mind, because sometimes we believe that science and engineering they has like solutions that are super nice, super simple for things, but not all the time the things are that simple. Even when you have the capacity to do that, even when you have the computers to do that, there are certain types of simulations, certain types of models that or theoretical understanding of that is not complete. And one example of that sometimes is the descriptions of fluids, as this is the air that acts like a fluid around the little golf ball. So that means that our current machines, they has these limits for making certain types of specific computation. And people, in behalf of that, they start to think about new creative solutions to try to overcome this problem. So that's why we're gonna talk right now about one of these creative solutions. And with that, I want to start introducing how we go from the classical computer to the quantum computer. So, in the case of classical computer, this traditional processing of information has been advancing a lot in what it has been the last cycle. No, we are talking about decades and decades of advance in the technology industry, from the vacuum tubes till the first computers that occupies a whole room, like the ENIAC by the end of the Second World War, and after the first computers that had transistors that were still super big, and we are talking about like the 56. So it has taken time to arrive to the computers with little chips that we have right now. But as we discussed with this simple example with the golf ball, there are certain limitations for this computer. One of these limitations is precisely the processing of large amounts of data, the transmission of large amounts of data. Um, Sometimes we cannot. I think one example of that, and you can correct me if I am wrong, is a case of the picture that I took of the black hole. People have to travel in plane with the hard drive that has all this data because it was so much that they simply cannot send him, let's say, like via internet. No, it was easier and faster to travel with the hard drive. So when we have a large amount of data, a large amount of data to process, or traditional methods start to face certain limitation. And we have another limit that is called the limit of miniaturization. I'm going to talk a bit more about that. Probably you have heard it before, and always that we talk about quantum computers, we tend to mention it. That is the Moore's law, no? So this is an empirical law that Gordon Moore formulated when he was working for Intel around the 65. And this empirical rule say that the number of transistors that are in the microchips, they double every 2 years. Okay, so if we have more transistor, we have a greater computational capacity. No, so as they double, all this power that the machines bring is doubling also. But if we want to put more of this transistor inside a chip, we also need to reduce their size. And that's why you have seen that, for example, well, if you if you are asking me like 30 years old, you have seen how phones used to be so big that now they are with sizes comparable, smaller than before. But even the same computers, like for example, here you have a picture of this computer that I mentioned to you before, the ENIAC, and right now you are listening to me with a computer that probably is in your table, no? So our apparatus, they are reducing their size, no? The problem is that when you start to arrive to these nanometric scales, even if you start to have like a great computational power, and even if you say like, well, the chips are less expensive, uh, you start to face certain complications. No, you could think like, well, by sure I cannot make like a transistor smaller than the atoms that compose it. No, okay, that's certainly true, but that is not the limit that you are facing. The thing that's happened is that when you get to the nanometrical scale, you start to have a quantum effect, like electrons that are tunneling between little gates, and that start to affect your transistors that they cannot be off. No, so that starts to introduce errors to them. So that means that even if you need more of them, even if you want to make them the smallest as possible, that start to cause you problems. So your solution cannot keep being like, let's make things smaller, smaller, smaller. If you really want to increase your computational power, you need to start to think about other types of solutions. And that is there where quantum computer arrives. So when we start to say like goodbye to these atomic limits that we are facing. So to start talking about quantum computer, we start to differentiate what is a bit from a quantum bit or qubit. So our bits are the fundamental units of information. They are in two states, 0 and 1, on and off, yellow and red light. It's simple two states that we use to storage the information. But in the case of qubits, that are the fundamental units of the quantum computer, you have more states to storage this, because you are only not going to have the state 0 and the state 1. Now, unlike the classical bits, you're going to start to have values that are multiple combinations of this, and that increase your power to make computation, because you're going to have more, let's say, more space available to storage the information. I'm going to give you an example of that. As I told you at the beginning, I am Venezuelan, so I'm using a Venezuelan coin to represent you this example. Like a classical bit can represent the two sides of a coin. But when you think about the qubit, it's not only one side and the other. It is all the possibilities that can be between them. Like when that example that you toss the coin into the air, and while it's in the air, it is neither one side or the other. It's like changing position, and you start to have different combinations. So like that is that idea of the qubit. But it's good that you start to ask yourself, like, well, what is the thing that makes qubits so special? What are different? Like, why they start to have more than one state that is 0 and one state that is 1? And that is due to two properties. One that is called superposition, and the other is called entanglement. And why we have these properties? Well, it's because we are going to a world that is infinitely small. So in our macroscopic scale, we know how the world functions. Like, we know where are stuff, we know at which velocity the stuff move, everything behave like the Newton laws. But when you start to decrease the size, you start to enter this tiny scale, the quantum world. That's how they decide to call it for this presentation. And then there you start to have effects, interesting effects that we humans take advantage of, that are very different from the ones that we have in the classical world. Okay, so these important features are quantum features that are only possible because we are in those scales. So the entanglement and the superposition that comes from being there is what they're gonna bring these powers to our qubits, trying to say it like that. Okay, but let's go a bit deeper into that. In the case of qubits, I'm gonna use as an example this cruel thing that by sure you have heard before, that is the experiment of the Schrödinger cat. But I think it's like even cruel is a good analogy to try to explain you from where it comes superposition. So imagine that you have a box, and a box that has a cat inside, and a poison that has 50% chance of activating and 50% chance for not activating. So while you are inside this box, and supposing that this is a world that functions with the laws of quantum mechanics, this is infinitely small world that we are talking about. As you have 50% chances that the poison activates or not, that means that you're gonna have 50% chances that your cat is alive or dead. So that's why we say that the cat is simultaneously alive and dead. Okay, but it's because you are in this quantum world, in this very tiny scale. Okay, so of course this is just an example, a cruel example, like that is a macroscopic object, well, a macroscopic living being. But with that, what I want to illustrate to you is that idea that the quantum realm functions different from our classical world. Okay, and it starts to have another properties that are what they make qubits special, and one of them is the capacity of having multiple states. And for that, I am using the idea of the Schrödinger cat. Okay, it's probably, if you try to think about it, like, let's say, in a more not but science well, like a more serious physical way, it's true that the state of a particle in the quantum world, uh, if we say it's like a wave function, no, and this wave function can exist in multiple states at the same time that are different from 0. So that will be, let's say, like a more formal definition of what is superposition. But for what I want you to know is that this is a quantum effect that allows the qubits to be in multiple states. Okay, now talking to you in more detail about entanglement, entanglement is really, really a fundamental quantum effect, okay? That allows qubits to be connected and to very, very connect between them in a way that what happens to one, the other is going to feel it immediately. And you can wonder, like, how is this possible actually? Like, for example, if I have a qubit in the sun and I have a qubit in the air, if you are saying that is something that happens to the one on the sun, immediately is gonna feel it, the one that is in the air. Um, how that happens? Well, first of all, is we suppose that they are in constant communication all the time. That will mean that that information travel faster than light, because for the light from the sun to arrive to the earth, it takes 8 minutes actually. So it cannot be in that way. They are not, like, let's say, in a permanent constant communication. So what is happens to one, the other is gonna immediately feel it. That is not the answer. You could say also, like, well, maybe when these particles were produced long time ago, they have some hidden variables that justify this, and that they determine their states. But also that has been proved that is not true, and if you want to know more about that, I will invite you to research a bit about the Nobel Prizes last year. But what I am trying to tell you with all of that is that this is an effect that is really a quantum effect and doesn't have an analogy with the classical mechanics or macroscopic work. Okay, so but it's still is something that is real. It's something that has been measured. Specifically with Chinese satellites, and they has measured this the record of the distance to see how entanglement are these particles is, I think, 1,200 kilometers. Okay, so it's something that is real, it's something that is being measured, and it's something that is quantum. Like, don't try to give it like a classical explanation. It works like that. But the interesting part about that is that allows qubits to be entangled, and with that you can explore multiple possibilities and stay simultaneously. So that will allow you to perform more precise computational process and more efficient in comparison to the classical system. So in this first part, what is the thing that I want you to remember? What is the thing that I want you to have in mind? It's just three things, really. The idea is that yes, our classical system has limitations. An accurate solution to that are the qubits. And the qubits are special by two properties, superposition and entanglement. Don't worry yourself right now if you don't yet get exactly what is superposition, what is entanglement. Remember, this is a pod science talk. What I want you to know is to start to manage this vocabulary, okay? So just those three things. There are limitations. Qubits are one of the solutions, and they are special because two quantum properties, features, superposition and entanglement. Okay? Okay, let's go then to our interlude, because till now it seems like it's a very interesting idea that we can put into practice. What are the challenges of putting this into practice? No, I'm gonna remind you, as I say in the introduction, this is something that I'm gonna talk to you fast, a bit superficial, because talking about this can be like a whole different talk, a whole different topic. So, our modern computers make mistakes. They do it. They sometimes has a bit that is zero, and ploop, they flip it to a one, or they has one, ploop, they flip it to a zero, and they has another types of errors that are not so simple to describe. Like, for example, how do you do to represent irrational numbers, like pi, for example, or like 1/3? You know, like this number that has many decimals, like 3.14, 15, etc., 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 etc. At some moment, with the last decimal, you will have to take a little approximation, and that makes that the errors accumulates in that decimal part. Okay, you can search about that in the internet. That is called the floating point error. But what I want to introduce you with that is that our modern days computers, they make mistakes, and the quantum computers are not different from that. We also have these mistakes of flip, like we pass from a state that is 0 to 1 or vice versa, and we have errors that are related to the phase. This is something that is under studying currently and that has different implications depending on the hardware and depending on the situation. So the quantum computers that we have nowadays, this new era, even if they look promising to certain types of problems, to solve certain types of problems, they are not completely perfect because these qubits that we say that were so special because of the superposition of entanglement, they can lose these properties over time, especially when they interact with the system. So we call them, these quantum computers that we have nowadays are the noisy intermediate scale quantum device. Okay, so that means that we want computers that actually this time before the qubits lost their special properties is longer, but that is something that is currently under study, and there are many possibilities for that. There is people that think like, well, we already have classical computers that can solve very well certain kinds of problems. There are other problems that is more challenging to them. So why don't we create like an hybrid model that use a bit of quantum and classical computing, like that adapts to the situation. There is people that think like, well, the solution is having more qubits, and there is people that think like, well, the best is to have like, let's say, I won't say like the perfect qubit, but let's have a chip where we have qubits that can resist longer before they start to lose their quantum properties. So that this is a whole area of research that is important because it allows us for in the future to have better quantum computers. Okay, but that is for you to be with that idea in mind, that they also face certain limitations that are under study. Okay, but well, I don't wanna, as I said before, I don't wanna finish like in a not super positive tone. So what I wanna present you right now is are like the real world application of these technologies, some examples, and that is super interesting because this is not only, let's say, like an idea, like a creative solution. It's something that is really transitioning to be something that is each year more present, a reality, and not only a curiosity. And in that sense, if you think like how you can make these qubits into real hardware, there are many companies and many laboratories that are already start to thinking in that, trying to create qubits, working with atoms or using quantum effects like supercomputing or using bosonic particles like photons. There is a whole ecosystem of people, laboratories that are into that. Okay. Uh, all of them try to follow something that is called the division criteria in some of these aspects more than the others. Basically, we want these quantum hardwares to be scalable systems. Like we want that we can put more and more qubits that is possible. We want to initialize these systems. That means that we can define the state zero very well. We want them to maintain these special quantum properties for more time, like a longer time. And we want them to make operation like your classical computers. That means to have like a set of universal gates. And by the other part, we want to extract information from the computer. So that means that we want to make measurements. So all these technologies try to accomplish that to create these hardwares. In particular, today, I just gonna talk to you about one of them that is the superconducting qubits, that are the ones that use the IBM, Google, and other companies. Okay, in principle, it's a very promising technology, and these qubits, they are based on selling to try to use this quantum effect that is called the principle of superconductivity. Conducting. So for that and to do operations in the qubits, they use like microwave pulse. Okay, and basically, if you search quantum computing in the internet, this is the image that is gonna jump to you everywhere. That is simply, let's say, like the refrigerator for the chip with the qubits is something, because for you to arrive to have this superconducting effect, you need to have this technology, these qubits in a low temperature. So it's for that they put it into these machines to guarantee that you're really gonna have these effects. So this is just to present you one of the hardwares that currently we have, that people are using. And with that in mind, people start to try to solve problems with that. One company that I want to put as an example, but there are other many companies that are start to use quantum computing, is the Volkswagen, this automaker, that they demonstrate a practical application from the use of quantum computing in the management of their traffic routes. Okay, but they also are has worked in parallel with other computers, like for example, this other one that I put here in the slides, that is Quantum, for creating systems for classification and recognition of image with the cars. So that means that companies that you have here already, for example, the Volkswagen again, that you already know, then they are starting to think about this technology to try to optimize certain of the tasks that it has inside the company. And that moves a lot of money. Like the global investment just last year, 2022, were around 30 billions of dollars. Most of this inversion goes precisely this into hardware, but that they are also implementations, part of the money that goes from the software. And it's important to talk also more about that, what happens with the software, because we know that we have already this noise intermediate system. We have sometimes this hybrid solutions that has a part with a quantum computer, another part with a classical computer. What can we do with that? No, there are already software developer kits that they can allow you to simulate and program a quantum computer. For example, you have the Qiski of the IBM, you have the PennyLane, you have the CERF from Google. All of them are based in Python, and you have actually a language for programming that, for example, the QCharm, no? So this is very interesting because it's start to offer you more than say like software as a service. It's like quantum algorithms as service, quantum computer as service, or quantum safety as service. No, so we can have many applications for the from the point of view of software currently. Here in this pod science talk, I'm just gonna tell you about three: the pharmaceutical part, the part with artificial intelligence. Sorry for that mistake. I put E. That is sorry, it's my Spanish. And after I'm gonna tell you a bit about cryptography, okay? Talking about the pharmaceutical point of view, the quantum computations has really potential for revolutionize this industry, for increase the capacity to develop new medicines. Why? Because you can do better chemical simulations for this industry. For example, you can take some of these technologies of qubits that we mentioned before, and with that you can simulate molecular systems that are complex. You can study how this can interact between them, and with that you can create better simulations or understand better the certain properties from molecules. And I will recommend you that you said, like a couple of weeks ago, there was a document that the Capgemini, this company that is in many countries made, talking about how they apply a quantum computer from the pharmaceutical sector. There are applications that come from the part of artificial intelligence, especially to solve differential equations. That is super important. And if you are someone that works in data science or machine learning, you know that solving differential equation is something that is extremely important from the industry, because we use the differential equation to modulate the heat that can go through a mechanical piece, or the flow of air, or a golf ball, or the flow of air through an airplane, for example. So we use methods that combines for example, the classical neural networks with the quantum computers to optimize computation from the point using artificial intelligence. So those are application of softwares that we can have. And currently also there are applications that go from the part of cryptography. What is cryptography? If you never have heard about this word, it's simply like how do you transform a message in a in a way that the information keeps private. That means that if Alice send a message to bot and you try to intercept the message, even if the person intercepts the message, they cannot understand exactly what was the thing that Alice was saying to bot. That is cryptography, how you keep that information private. And for that, there are many protocols and many current things that people do, okay? Let's suppose that you have a little spy that is called Eve, and Eve wants to know what is Alice saying to boss. There is a protocol that Alice can use and bot can use also to maintain this information secret, that is called the RSA protocol. No, so let's imagine it like this: you have a box that has a special lock, and the lock is closed and it follows this RSA protocol. That means that for you to open this, you will have to learn how are the prime factors of a big big number. So that means that it's a protocol that is based on map. That is usually a task that contains a lot increasingly a lot of time for a classical computer to do. it's difficult to try to find what are the factors of this number. But if you do it with an algorithm, a quantum computer algorithm, and here I'm just gonna let you the name. I am not intended to explain to you in detail. It's just for you, as I told you, to be knowing a bit the vocabulary. That is called the Shor's algorithm. You have the potential to break this and know uh, what is the message that has been sent from Alice to Bob, no? So even if we have these protocols like the RSA to protect our security, quantum computers start to show that it could have some certain degree of advantage to resolve, for example, mathematical problems and get what is the message. Uh, and I am not saying this to get you scared or alarm you, saying like, it's gonna break cryptography. Like, there could be also other types of technologies that could break cryptography, and the thing is not panicking and get scared. It's like to think, how can we solve that? We can solve that also using the same quantum computer. For example, we can create a quantum channel to send the information, a quantum channel that, for example, is if the spy try to see what Alice is saying to bot, they can know that she's there and they can abort the protocol. Okay, precisely because this channel is based in properties that come from our quantum mechanics work. So right now there is people that is trying to work in this area of cryptography from the quantum point of view, even in areas that are post-quantum cryptography, so that we can detect when there is an intrusion and we can protect our information. Okay, so it's not to get scared about that. Okay, so well, what I need you to remember from this second part, what I need to you for you to remember about this second part is just like 5 things. There are many types of qubits. There are several leading companies in this area from the point of view of hardware, from the point of view of software, and that has a global economic impact. There are a lot of investment in that, and also from the academic point of view, we have more master and more PhD that are in this area. This has a promising applications from the part of software. One example we have seen the cryptography, and that pose challenge to the current cryptography. I want you to be careful with that idea. Also, I don't want you to get out here thinking like just quantum computers are just simple faster. It's not just saying like they are simple faster than classical computers. For certain type of problems, they solving better than a classical computer, okay? And that this is an area that is in constant research all the time, and that is changing a lot, okay? So if you can understand this thing, that is what I want you to remember, and I invite you that if you are interested, you keep checking about that, okay? And now, just to give like a last summary, yes, there's many people working on that from the point of view of hardware, from the point of software, you know already some of them, Google, Amazon, IBM, Microsoft. There are people that just work in the software. There are others that work with the hardware. For example, Intel, or in the software, multiverse computing. But there is a whole ecosystem of many companies and great people that is in this area using already these technologies and creating new resources with them. And there's people as Womanium that they are making the effort to educate others as me or as you to know more about this technology. That I want to mention also the people from Qworld that they are putting a lot of effort to create interactive notebooks where people can form themselves and learn more about this. And now, look is what happens when preparation meets opportunity. What can you do to prepare yourself in this area? And I know that I told you that I was not going to put you equations, and I promise you that I'm still not going to put you an equation. But what I just want to mention to you is that, yeah, like if you are curious about this area, it's good that you learn a bit of linear algebra. Why? Because linear algebra first is used in machine learning and in other areas of mathematics and in quantum mechanics also. And we use it in quantum mechanics because there are physical properties in quantum systems that are just justified by the use of linear algebra. And I want to say, let's say a more formal way, is saying that these wave functions that describe the particles, they live in a Hilbert space, which is a mathematical space where we can define a scalar product. And for you to understand that, that means that you need to know a bit of linear algebra. And that is just a simple example. We can include then other things like the position, the momentum, the energy. besides the joke that I try to put here with this meme, no, linear algebra is not only about matrices. In quantum mechanics, sometimes we talk about function space, and those are not matrices. We talk about operators applied to functions. That is not a matrix. It's just simply that linear algebra is an important part of mathematics, and with that you can define vector space operation within this sphere. So it's a representation that is very useful for many modern technologies. And if you wanna, work more into this, know how to apply it, it will be good that you learn about that. But in the other side, as I mentioned to you before, there are already some software developer kits and free resources about them in Qiskit.PennyLane. And the most interesting part about that is that they are all based on Python. So if you wanna know more how to use these things, how to play with them, and work in projects with that, is important that you learn Python, okay? And I will let you with some quantum computer books that I think that are very interesting. This, I would say that this green one here is like a classical recommendation that you're going to find everywhere, but there are other books that are more like quantum computing with Qiski only, that summarize very well what are the basic things that you need to do. That is the case of this Macaulay Collins book, very recommended. And me personally, I love this book by Venkat Senwara and Kasirahan. I hope that I say the name well. It's a very amazing book because it's a book that is addressed to all the audience, like the people that come from the software engineering part, the people that want from the computer science one, and the people that come from the physics. So there are many things that you can do here in this new field, and it's a great opportunity. And the most important is that you are someone that is creative. Like, you don't need to necessarily be someone that does computer science, software engineer, or you are a physicist. Like, if you want to participate, there is an industry that needs people from different backgrounds, okay? And one example that I want to let you with that is for me an example that represents really the word creative, is this game that is going to be available in Steam next year, that is called Quantum Odyssey. In that game, you have people that come from physics, people that come from computer science, and you have all the other things that involves to do a video game that has a stunning visual art, very beautiful music. So this is a world with people that come from different backgrounds, and it's a representation of what it is means to be creative, and it's an educative game. Like, it's a very, very fun puzzle game for you to learn the concepts of quantum computing. So that's why I invite you to don't be scared. Try to think that this is a field that is growing and is open to many people around the world. So with that, I want to finish this divulgative talk, virtual divulgative talk. So thank you so much if you listen to this until this point, and if you have questions, you can contact me in my blog. Okay, bye bye.